Another example of being able to eliminate the parameter for this parametric, we have x equals 3 sine squared of t and y equals 3 cos squared of t. And we go from the domain 0 to 2 pi. Now, this is a tricky one because in this case, if we tried to solve for x or for y, we would have to divide by 3 and then take the square root, and that would become really ugly. And then we'd have to use maybe like some really ugly trig substitutions or trig identities. But here's a way that we can try to be able to plot this rather easily. So first thing we're going to do, let's plot a few of the points. So when t is 0, that means we get x is 3 sine square of 0, which is just 0 since sine of 0 is 0. And then y is going to be 3 cos square of 0, which is going to be 3 times 1 square, which is 3. So we know that one point is going to be 0, 3. Now, another point, let's just go ahead and use pi. All right, I know 2 pi is the terminal point, but just to show you what's going on with this, okay? And so x would be equal to 3 sine square of pi. And we know sine of pi is 0. And then y would be equal to 3 cos square of pi. Now we know that this is going to be 3 times negative 1 square, so we have 0, 3 as well, right? And then finally, if t were equal to 2 pi, we're going to get the exact same thing, okay? So we keep getting 0, 3, 0, 3. And then if we were just to plug in 2 pi, x equals 3 sine square 2 pi, which is 0, and y equals 3 sine, or cos square, excuse me. So 3 cos square of 2 pi is also going to be 3. So it seems like that we keep getting the point 0, 3, but that's not the only point that's going to be on this curve. We just have to be careful about which points we pick. All right, so 2 pi is equal to 3 as well. All right, now what we can do is we could just add these together. Okay, so we would have x plus y is equal to 3 sine square t plus 3 cos square t. But we know that this is a Pythagorean identity if we factor out the 3. So x is going to be equal to, or x plus y, excuse me, if we factor out that 3. So we have x plus y is going to be equal to 3 sine square t plus cos square t. And we know that this is 1. So we get x plus y is equal to 3 times 1, or y equals 3 minus x. Okay. Now, one thing that we should be concerned with is what are the largest and smallest values that x and y can get. And it's clear that the smallest x that we can get is 0, all right, because it's a square. Okay, so we know that x is going to go from 0 to something, and then y is going to go up to 3, okay, because we know that the regular cosine function can't get any bigger than 1, all right? Because it's squared, it's going to be 0. And then to get 3 out of the sine, t would have to be equal to pi halves, all right? So if I throw pi halves in there, we get x equals 3 sine square of pi halves, which that's going to be equal to 3, all right? So sometimes it's helpful, especially with trigonometrics, to see what the domains are going to be, okay? And so the graph of 3 minus x, now we have to be careful with this, because if we were to look at the regular graph of y equals 3 minus x, well, it would look something like this, okay? So we would have the point right here and here, okay? And the regular graph of 3 minus x would just look like this, okay? But that is not the case for what we want, okay? So for what we want, we're going to erase this, and we're going to erase this because we're only concerned with the domain like this, okay? So this is what the graph looks like. Now, the orientation for this is actually pretty weird because if you'll notice, it starts at 0, it's going to start at the point 0, 3. Okay, so it's going to start here, right? And then it's going to go down. Okay, and it's going to end up here. So this is when t equals 0, and this is when t equals pi halves. But what it's going to do is it's actually going to go back and do this sort of thing. Okay, so that doesn't look too good, but let me redraw the graph. Okay, so I already draw the graph one more time for this, and I don't want to spend too much time on this one. We do have another one that I want to get to. But looks like this, and initially, this is what the function is doing. However, another time, okay, let me just plot another graph. It's going to do this when t equals pi halves. Then it's going to go back, and right here, this is when t is equal to pi. So essentially, it's basically, if you think about like a conveyor belt, if it was just like a really flat conveyor belt, it's just going back and forth a few times. I graphed it in fooplot, and this is what we get in fooplot. All right, but again, it's doing this sort of thing where it's going down and then up and then down and then back up. Okay, so it actually has almost two traversals of this. Now, another example, and this one's a little bit sneakier, of being able to eliminate the parameter is this x equals 2 sine t, y equals 3 cos 2t. All right. Initial point, we're going to have t equals 0. That's going to be x equals 2 sine of 0, which is clearly going to be 0. And then y is going to be 3 cos of 0, which is equal to 3. All right, so the initial point on this is going to be 0, 3. Now, sometimes it's helpful for you to get a few points in between. Then you can go ahead and eliminate the parameter. So let's use t equals pi halves. All right, and so that would be x equals 2 sine of pi halves, which is going to be 2, since sine of pi halves is 1. And then y is going to be 3 cos of pi halves, which is 0. Right? And again, we get some other points on here. So another point is 2, 0. Right? So just kind of giving you an idea of a few points. And then finally, like the terminal point, when t is equal to 2 pi, that's going to be the same thing as when it's equal to 0, okay? Because it's coterminal. And so that would be the point 0, 3. Now, here's how we're going to eliminate the parameter for this thing. We can't add these together yet, but what we could do is we could square both sides. So I can go ahead and rewrite x as x over 2 equals sine t, and I could divide by 3 and get y over 3 is equal to cos t. Then I can square both sides, right? So I could square this and square this and square this and square this. And I'll get x squared over 4 equals sine square t. And then I get y squared over 9 is equal to cos square t. And then I could add those together, just like we did previously, because now we have that Pythagorean relationship. And then we have x squared over 4 plus y squared over 9 is going to be sine square t plus cos square t. And we know that sine square plus cos square is 1. So we get x squared over 4 plus y squared over 9 equals 1. All right, now we have to think back to pre-calculus a little bit, and this is actually going to be an ellipse. Okay, and what you could do is you could just think by substituting some values back into this. So let's say, for instance, x were equal to 0. Well, then y would have to be equal to plus or minus 3, right? Because the only numbers that you could divide by 9 to get to 1 are going to be plus or minus 3. And then if y were equal to 0, x would be equal to plus or minus 2. Because again, if this were to go away, right, then the only numbers that you could substitute back in for x to be able to get x squared over 4 equal 1 would be plus or minus 2. Right? And so if I were to graph this, then we have y is 3 and negative 3. Right? So we have these points and these points, or this point and this point, excuse me. And then we have 2 and negative 2. So we have here, and again, not the scale, but again, we're going to use technology. And then over here. And so we get this ellipse as best as I can. I know it's not going to be good, but you get what you pay for. So now the other thing that we have to remember is the orientation. And remember, it starts at the point 0, 3 and then goes to the point 2, 0. All right, so this function or this parametric is actually going to be counterclockwise because it starts up here and it goes down to here, right? And then if you were to just plug in another number like pi, okay, that would give you 0, -3. All right, so it's doing one of these animals where it's going counterclockwise. Okay, so last thing we're going to do though is we're just going to verify what the graph looks like by using our technology. So we have 2 sine t, 3 cos t. So we have 2 sine of s and 3 cos of s. All right. And notice that it does indeed give us a nicer ellipse. Okay, much nicer than the one I drew. However, this is the one we did by hand, and it gave us the orientation. Okay, and the orientation is difficult to get by just looking at a regular graph. Okay, so that's how we can eliminate the parameter. Okay, a couple sneaky ways, but pretty cool that we're able to do this. So we're going to continue our study of parametrics with moving into calculus in the next video.